Last time we did the PCA, principal component analysis. So for supervised learnings, actually there are two main topics. One is the clustering, and the second thing is dimension reductions. Dimension reduction is like here. We start with the motivations, and I think you all know what's the advantage or benefit of have some re-representing the data set in the raw dimensions. And there are many ways actually for dimension reductions, but one of the famous and the most useful one is principal component analysis, and that's what we did. And I derive like here to maximize the variance. That's the objective for that. And another thing that I want to mention is these are the equivalent. Maximize the variance or minimize the sum of squared errors are the equivalent. And I think I proved that. And let's see. And this one is kind of clear. I want to tell you guys that PCA and the linear regressions, as you can see, looks for illustration, it looks pretty much the similar. But for linear regressions, we want to minimize in these directions, and on the other hand, the principal component on PCA is make projections on U directions and minimize the sum of errors in that directions. So those make a big difference. And I think here, that's where we stopped. So I want to continue on from now on. And I guess from now on, you guys can understand the motivations and benefit of dimension reductions. And I want to share or show you, at least for me, it's one of the fantastic examples for PCA. And let's see what it is. And suppose we have, suppose we have, because here, let's think about this kind of the physical experiment, or is related to mass. Over there, we have a mass spring system. And I guess as a mechanical engineering students, probably like you can model it. We have mass and spring constant K. We know that, suppose we assume that there's no frictions, things like that. And we know that it's oscillating, like that. It's oscillating. It's gonna have periodic behaviors. I mean, I hope that you guys are aware of the vibrations, and we know that it's oscillating. And if you plot it in time, probably like this kind of behaviors, we already know. I mean, here, I guess, how do I say, we have this M, and the external force, I suppose, is in displacement X, and then in that directions K, and that's Kx. That's the external force by spring on mass, and so that's the accelerations probably x double dot. So we know that x double dot is equal to minus kx. So if we write it down, x dot plus kx is equal to, that's the ordinary differential equations that represent these dynamic behaviors. That's a physics. Okay. And what we're gonna do today is, let me say we have in gravity. So we put the spring mass in a vertical way. And if I release it, probably it's going to oscillate it like that. It's going to oscillate it. You know that, right? So let me see. Suppose this is equilibrium point, probably like oscillating like that. That's what. So suppose we conduct the experiment, and I want to measure the displacement. I want to measure the displacement. How are we gonna do? How are we gonna do? So probably what we can do is that we can put the camera right there. Say this is camera, and so spring is oscillating like that, and I'm gonna put the camera, and then we can measure it, the displacement or movement or positions. But say, so what if the camera is slightly tilted, and you, right? So in that case, say if the camera is tilted in videos, probably the mass is gonna oscillating in that directions. So it really depends on, we have to put everything in exact positions and exact directions to make sure that everything is aligned. Okay. And so in order to measure it, there's some, if some have noise on it or uncertainties, and we're not gonna get the exact like a measurement or observation that we want to have. So let's put more cameras. Say we have camera A and B and C. I mean, just using your smartphones, it does, and just like hold it by your hands, like any direction, it's okay. And it's kind of, you don't have to be aligned. It doesn't have to be aligned, and it's okay to be tilted. And I'm gonna ask you to hold it like as firm as possible, but it's okay to have some kind of like shaking behavior. It's okay. So I asked TAs to conduct the experiment for you guys, and this is how we got. And I don't know which camera is A and B, C. Say suppose this is A and B and C, and just intentionally, like we don't align it, like just have that, and let's see. And this is the measurement from the cameras. So like, so the camera A is like, I don't know, like this or that way. Anyway, it's B is like totally opposite way. And so, but the key thing is that we use 3 cameras instead of single camera. And the reason why I put red colors on it, because I want to extract the positions or X, Y, or coordinates using the color. So that's the only reason. And we extract the positions from the image, right? And let me see, say this is the image of X and Y. I would say channel 1 and channel Y. So this is the coordinate in channel 1, and we have another X and Y, and channel 2, we have another one. So at the end, from the image, what we're gonna do we're gonna have time series X and Y from the first camera, camera A, X and Y from the camera B, second cameras, and X and Y from camera C. So eventually what we kind of do is that this is what we're going to get out of. So we have 6 channels. Are you guys with me so far?
Yes.
Okay. So let me ask from here. So what's actually here we have six, I'm gonna say time series. But actually from the physics, we know that how many time series actually that we need?
One.
Just one, right? Just here, if you define it, this is X or define it Y, well, it doesn't matter, but this is like the only direction that we are interested in. And if it's time, probably this is gonna the displacement that we want to have. But since we put 3 cameras, we have 6 time series instead of 1. Okay. And key thing is that here, even though we have 6 measured observations, we know that the original system is 1. That means from the physics, we kind of know that these are correlated. These are correlated. Why? We don't have to compute the correlation coefficient. We know that. We know that from the knowledge of the physics that we are measuring it. So we know that this is actually originally from 1. Then from 6, how can we get any ideas? We know that these are 6, but these we know that these are like correlated. And many of them are redundant. Any systematic way that we can extract 1 out of 6. Now we can do dimension reductions, and we can apply the PCA. Let's see how can we do. So now it turns out the measurement we can reformulate it in multivariate because we have 6 channels. So multivariate time series, like from camera 1, camera 2, camera 3, X, Y, X, Y, X, and Y. And this is the coordinate dimensions that we have. And again, I want to make it skinny matrix. So at the first time instance, we're going to have 6 component or 6 measurement. And says time 1 and time 2, we have another one. So it's going to be like that. Right? It really depends on, like, you're gonna take a record like 10 seconds or 20 seconds, 1 minute. It really depends on, right, the length of the movie clip that you have. So you guys can imagine like this will be big skinny matrix. Now I want to do PCA. We can do, you guys remember S is sample covariance matrix. So if this is large X transpose X, it's gonna be like, let me see. Or I'm not sure whether this is, let me see, X, let's see, like that, or X transpose TX. This one is, say, M over 6. Yeah, So this is S, and of course you have to do like that. And this is the formulation for principal component analysis. Actually, we can compute it, but you don't have to do. You don't have to do computation by hand. So we can use Python. So we know that it's from the eigen analysis. So we can compute. Let's compute the eigenvalues and eigenvectors. And this is what we got. So this is the eigenvalues. And this is the lambda 1 and lambda 2, things like that. Then from here, you guys can get some kind of insight. How many axes do we need for low dimensional space? This is dominant, right? So probably 6 to 1, probably it will be, you guys can get some kind of hint from the plot of eigenvalues. It's different from k-means, but very similar. For PCA, the magnitude of eigenvalues is gonna give us some information that the first how much that the first eigenvectors contribute and second eigenvectors are contribute. So compared to the first, rest of them are pretty much, you guys can ignore them. So let's make projections on the principal component, which is the first one. So that's what we did. All right, so from 6, actually we're gonna have 6 components. So we did the projections on, so actually this is the one from first, and these are from second to the like 6th right there. So out of these three, the plots or figures, it's really obvious that the first, the component, principal components is dominant. Which makes sense, because if you think about the original, the problem of the system that we have is that the oscillating, the mass spring. So actually this is kind of then what is this? Any kind or some kind of noise induced during the measurement, because I'm gonna hold the smartphones. So I mean, I'm gonna like do some shaking, like, okay. So that's why we have some kind of noise. You can think of noise or disturbance, but it's okay, because from the PCA or dimension reductions, we know that those are the noise only. So we only extract the dominant behaviors. So this is the example that I want to share with you. And I guess this is like one of the best example or demonstrations that we guys can think of to see the benefit of having dimension reductions. You guys can see? So, okay, this is the examples. And let's move on to the PCA is let me see, suppose you have this kind of time series data set, and you put 3 sensors, and R of 1, R of 2, and R of 3. You measure it over time, and so supposed to like end up having these 3 different time series. I mean, I guess just by looking at these, I don't see any problems. I don't see any issues. And we might have, so we gonna plot with the different representations. So it's R1, R2, and R3 coordinates. And over time, we plot like that, like we made a trajectories. And let's see whether this is make sense or not. So just in R of one directions, gets smaller and gets bigger and gets smaller, gets smaller and gets larger and gets smaller, right? And in R2 directions, gets smaller in R2 directions, so gets smaller. In R of three directions, larger and smaller and larger, larger and smaller and larger. So from what I did is that I hope that you guys can, these two have the same represent the same thing with different representations. And sometimes in this, say, the trajectory, we thought this is like trajectory in three-dimensional space. That's general case. But sometimes it turns out it's only of course it's a trajectory in three-dimensional space, but in two-dimensional hyperplane, like this. Then you don't need three-dimensional space representations. Only thing you can do coordinate transformations with the dimension reductions. Say this is S of 1 and S of 2 over time. So in S of 1 direction, smaller, and no, S of 1 in that directions gets larger and gets larger. In S of 2 directions, like that, like that. So this is final representations. So starting from here, we end up, the only difference is that over there we have three sensors or three axes, and there is your only thing is you need two sensors or two axes. Simpler representations, and we can reduce the cost because you want to have only two sensors instead of three, and much intuitive. So that's why, another example that I want to show you that the dimension reduction is most of the time it's beneficial. Okay, so that's all I have. Dimension reductions and principal component analysis. So we covered how we derive the principal component analysis, and I show you some of the most interesting examples using spring mass systems. Actually, what I recommend you guys that you guys can at home, what you can do is that, you have to get some kind of spring and mass systems, you have to make it, but from like with your friends, you can measure it like, using your smartphones. Actually, you can do the same thing actually with what I demonstrated here.